Today I'll be talking about how neural networks actually learn, and we're going to talk about a concept called gradient descent. Let's talk about a real-life example of handwriting recognition, because it's simply easy to visualize. First, we initialize the network where each node in the input layer becomes a value from the image. Here we will have 784 given the number of pixels. Each node in the output layer corresponds with a label, in this case, a number we're trying to predict, and here we have 10. And we're going to give our network a blank slate by randomizing weights on each graph edge. We'll also include our activation functions for the hidden layer nodes and the output layer nodes. Remember, there are actually 784 input nodes, not just 3. We'll multiply each pixel value by the value of each weight. The product of each incoming signal will be summed and applied to an activation function. This process is then repeated for the second layer. We take each training sample, make the calculations, and then see how much our prediction is off by. We need some sort of loss function or something to measure error to let us know how we did. In this case, we'll use this loss function. And the values are shown here. So how can we update the weights in all layers proportionately? In other words, how much does the error change in respect to each weight? Before we answer that, let's first distribute each error value from the loss function back to the previous layer. We can use the weight values to determine how much error each node is responsible for. The larger the weight, the greater the node contribution. This is part of back-propagation. Now we sum each of the edges attributed to each hidden node. For example, 0.12 plus 0.41 gives us 0.53 for the top node. Okay, so now we know the distributed error for each node in each layer of the network. We still don't know how the weights should change. And before I dive into a more technical explanation, just remember we're seeking the precise weight values to minimize error, and that's it. If we were to take a simple squared loss function and graph with respect to just one weight, it's pretty easy to find the value of this weight on the graph where the error is the lowest. It's the point where the slope is 0. So how do we find the slope when the rate of change is not constant? We need to find the derivative. And a derivative is just the slope of a tangent line at a given point on the graph. Then, once we have this, we'll set this derivative to 0, and that gives us the weight value of the lowest possible error. However, when we add significantly more weights, and when the loss function becomes more complex, finding the minimum is not easy. Instead of this simple 2D parabola, we could have a loss function or a loss landscape that looks something like this. Our loss landscape might not be quite this rugged or look just like this for a simple network, but we'll still need to introduce a concept called gradient descent to find the weights that minimize the cost function or error. So let's step back for a minute to better understand this concept. Imagine you're a camper who is dropped off at a random point in a mountain range. You have no prior knowledge of the terrain, no map, and you can only see what is immediately around you. We'll assume that the temperature gets very cold at night, and the lower you go, the higher the temperature. So you're seeking the lowest point. You're given a few guidelines. You need to walk downhill and traverse the steepest path first. As terrain becomes less steep, you need to take smaller steps until you eventually get to the lowest point without walking uphill. Eventually, you get to your destination and you signal your sponsors. This process is repeated with other campers, and we find through all these signals what the true lowest point was on the other side of one of the mountain peaks, and those coordinates are captured. In our case, instead of optimizing for temperature, we're optimizing for performance. So the descension in height is actually a reduction in error of the network. So how do we actually do this? Given a random position along the loss function, we need to find the tangent slope or derivative of the error in respect to the weights. Once we find the slope, we'll know two things. A, the direction of move, based on whether it's positive or negative, and the magnitude to move. In other words, we take a step proportional to the slope at the given point, and we step in the direction away from the gradient. And we do this iteratively until the slope approaches 0. So the non-technical translation is we're just going to decrease the error proportionally to slope in the direction that leads to a lower value. So here we have the same derivatives as with the previous example, which give us the slope of the tangent line. We'll multiply these derivatives by some learning rate, which we'll represent with the letter sigma. That's just the size of our steps. Then we subtract the product from the old weights. So this just gives us the new weight, which will be a lower point. And all we're doing is updating these weights. So let's plug in the weight values here, then make our adjustments on the graph. We're moving down proportionally to the gradient times the learning rate. In summary, remember what we're asking here. How much does error change with changes in the link weights for the previous layer? And that's it. We're looking for the partial derivatives by isolating each weight. Okay, so all we're doing here is we're attempting to derive the error in respect to each weight between the hidden and output layers. And so all that really means is we take this error function, which is just our target values minus what's coming out of those output nodes, and that's our squared loss function. And then from there, we're just differentiating to give us this equation. And the next thing we need to know is, how is output determined? Well, the output's already going to be in any code that we have. This will already have been calculated by the neural network. And that's just this slide right here. And so we can plug this in. We can break that formula down for how we're actually getting these output values. And then we differentiate again to give us this equation. And remember, we do the same to derive the values from the input layer and the hidden layer as well. And this looks really similar. And so you put all this together, the code is actually pretty simple. And again, we already have these calculations from feeding data forward into the neural network itself. And remember, this ends up just being a large matrix operation. So all we're doing here is we're looking at the gradient. And for the gradient, we're taking the dot product of two things. We're taking the output error times final outputs times 1 minus final outputs, 1. And the second thing is the hidden outputs, so whatever's coming out of that hidden layer of the neural network. And then we're taking the output weights and updating them. Then we repeat the process with a new sample or batch of samples. Once we get through the data, we may repeat the process with all samples again. This is called an epoch and really depends on the problem. Now that we have our weights, we can productionalize this model and start making predictions.